invitation to speak here. Thanks for the invitation to speak here. I will say that after this talk is over and the questions are over, I will go and have breakfast. Well, a few minutes ago, it was still dark here. I'm not sure if that is now or not. Another thing I should say is that I put in the abstract several things, and I'm actually only going to talk about one of them here, which is for various nice Banach spaces X, that if you have a homomorphism from bounded operators on X to bounded operators on Y for some other Y, which is surjective and is also injective. I mentioned things about when bounded injective homomorphisms automatically have closed range in the abstract, but I won't get to that. So here is an outline, so introduction, something about previous results, which are due to Banach. A large Cuntz system in a special case. So I'll explain what that is, or by example, really, it is related to the Cuntz algebras in the previous talk, what to do with it, and then a more general case and some consequences. I'm not going to prove things in the general case, but the special case is simple enough that I'll actually go through one proof. So here's a bit more careful statement of the of what we're going to do. So the idea is that for some choices of X, and some of these were already done, and we'll get some new ones, which are not too far from classical spaces. Whenever Y is some other Banach space, and you have a surjective homomorphism from bounded operators on X to bounded operators on Y, then it's also injective. And some comments. This property was introduced by Horvath under the name SHAI, standing for surjective homomorphisms are injective. That's applied to the Banach space. He proved that it holds for little LP and for some other spaces, and asked about capital LP. And he also did other things, which I'll mention shortly. Let's see. There we go. So a comment is that such homomorphism is automatically continuous. This is an old result of Barry Johnson. The conclusion is, of course, then that phi is bijective, and now a very old result of Untitled says this implies that X is isomorphic to Y. This is sort of the opposite direction from trying to realize many Banach spaces as Calkin algebras of, say, separable Banach spaces. That problem was considered, or one instance of it was considered in the talk of Motakis, what was it, 2 days ago in this session. I should also maybe mention that the Cuntz here is the same as the Cuntz in the talk I gave yesterday in a different session. On the other hand, there's otherwise no overlap. So some further things in the introduction. So there are certainly some separable infinite dimensional Banach spaces without the SHAI property. And I mean, there are more examples than this, but here for really trivial reasons, although proving them is highly non-trivial, namely that there are surjective homomorphisms to the complex numbers. James spaces, those are old. Gowers-Maury space, Argyros-Hayden space. Horvath's paper actually lists some more, which I won't go into. And more generally, for every separable reflexive Banach space, Horvath finds a now non-separable Banach space Z with a surjective homomorphism from L of Z to L of Y, which is not injective. Sorry. The methods Horvath used include semi-simplicity and minimal idempotence. Our methods are very different. They're motivated by the structure of the Cuntz C-star algebra O infinity, which is related to O2 from the previous talk. This algebra is generated by isometries in the C-star sense with orthogonal ranges. And so here are some relations which you would have seen at least alluded to in the previous talk. The fact that they have orthogonal ranges says basically if you apply one of the isometries and you take the corresponding co-isometry for a different one, then the answer is 0. But if it's the same one, then you just get the identity back. I forgot to actually state, though I wrote on the slides, this is joint work with Bill Johnson and Gideon Checkman. And the sort of part that I contributed to it was this idea from Cuntz algebras. So here is the motivating observation. There's an isometric isomorphism, which I called capital S, from little L2 of the non-negative of the positive integers to the closed linear span of the isometries, which sends a sequence alpha to just the corresponding linear combination. And then there's a corresponding map from L2 to the linear span of the corresponding co-isometries, the Sj star, and one has S of beta star times S of alpha is the usual scalar product on the Hilbert space little L2 times the identity. So that's really some kind of generalization of the statement above. This part here is saying that when alpha and beta are both standard basis vectors for little L2. Okay, so I'm going to talk about little LP, bounded operators and little LP modulo compact operators and little LP. I wrote K for little LP, but of course this is the same as the approximable operators, which is the closure of the finite rank operators. And I'm going to describe what happens there because it's relatively easy to see. This case is actually already covered by Horvath's paper. And the reason is basically that, well, a bounded operator in LP has only one non-trivial ideal, namely the compact operators. So a surjective but not injective homomorphism would have to induce an isomorphism from the Calkin algebra of little LP to the bounded operators on Y. On the other hand, L of Y has minimal idempotence, but the Calkin algebra on little LP doesn't, so they can't possibly be isomorphic. Okay, I'm just going to use N for strictly positive integers. The standard set theory result says that there are 2 to the Aleph 0 infinite subsets of N. Well, so much so good, but they're also effectively, so they are pairwise almost disjoint, as the intersections are finite when the indices are different. So I simply take them to be indexed by some index set of cardinality 2 to the Aleph 0. And then for each of the indices, I'm going to choose a bijection from N to the corresponding set. Then there's an isometry on little LP, which sends a standard basis vector delta N to the corresponding one for Hj of N. And there's a reverse, which in the C star case would be the adjoint, which is also has norm 1. And what it does is it basically undoes what what Vj does when your standard basis vector is in the range, and it kills all the other standard basis vectors. So now we're going to let Q, I should probably call it Q of little LP, but I will just call it Q, and I'm going to let pi be the quotient map. And then we're going to set Sj is pi of Vj and Tj is pi of Wj. And now these things are isometries in the algebra. Well, of course, you want to make a proper definition of that, which I didn't do, which have now pairwise orthogonal ranges, orthogonal in the algebraic sense, namely Sj, Tj is an idempotent, and the product of two distinct ones of these, of two of these idempotents for distinct indices is 0 in either order. Okay, here's a repeat of the setup that we have. What Hj is, Bj intersect Bk is finite, and what Vj and Wj are, and what Sj and Tj are. And we'll let Q be the conjugate exponent. And so here's the proposition. And I called this a Cuntz system. I haven't formally defined a Cuntz system, and I won't. But here, these elements Ej, which are Sj, Tj, are norm 1 idempotents, which have product 0 for different indices. And in fact, a stronger condition. Well, this is equivalent in C-star algebras, but not obviously. So here, namely Tj, Sk is 0 when j is not equal to k. There's uncountably many of them, remember that. And then there's an isometric isomorphism S from little LP of the index set to the span of the SJ, which basically sends standard basis vector to SJ. There's a corresponding 1T from little LQ of J to the span of the reverses, which has the same kind of analogous behavior on the standard basis vectors. And then furthermore, the standard duality between little LP and little LQ is determined by just multiplication in the algebra. T of beta, S of alpha is now pairing of alpha with beta. And now there's no longer any adjoints in it because I don't have a star to get conjugate linearity. So it's just pairing of alpha with beta times the identity element of the algebra Q. Okay, so I'm going to describe the proofs of these parts. This is basically the only proof that I will do, but it shows how things how all these things come out. So here is just a reminder of the setup that I had. So here is the repeat of the first part of the proposition. Tj Sj is 1. The elements Ej are normal idempotents, which are orthogonal, and so on. So in fact, with the way things were defined already, Wj Vj is equal to 1. And Vj times Wj is multiplication by the characteristic function of Bj on little lp. Well, now Bj intersect Bk is finite when j is not equal to k. So the image of multiplication by that in the Calkin algebra is 0 because it's a finite rank operator. And so that's what gives you Ej, Ek equals 0 when j is not equal to k. I realized, yeah. One thing I should mention is I like I say, I put up in the chat the URL for a handout version of the slides, and I will replace that with one with misprints corrected when I get to it. Okay, so for item 2, well, here's the setup again. Here is what item 2 actually claims. There's an isometric isomorphism from little lp of the index set to the span of the SJs, sending basis vector to SJ. And so here we're going to restrict to finite sets in the index set and prove things there. And then once you have that, well, then this gives you the result for the finitely supported functions in little lp of j. But then since we already have isometric, it extends by continuity. So I'm going to pretend that the sets Bj for j in this finite set are disjoint. This is not actually true, but you can, for a finite collection of indices, you can replace n by some suitable cofinite subset, so that and similarly replace the Bj's by cofinite subsets, which I didn't write, so as to make that true. So I'm not going to go through that part. But now, sorry, question? Okay, so now I take something in little lp of the finite set. I look at Xi in little lp of n, and the supports of the elements when I apply Vj to Xi, these are now disjoint. They're still disjoint when I multiply them by alpha j. So now the norm, the pth power of the norm is just the sum of the pth powers of the norms of the pieces because they have disjoint supports. But then the norm of Vj Xi is the norm of Xi. So I end up with the sum of the coefficients to the pth power times norm Xi to the pth power. I simply take 1 over p roots. And in fact, what you end up with is that S sub f of alpha is actually a scalar multiple of an isometry. And this implies the claim. Okay, for 3, which is the one with the TJs, here's the setup. Here is the claim. This is a little bit trickier. You now effectively have a scalar multiple of a coisometry in some sense or other. But again, and so things aren't quite so simple to write. But again, we'll restrict to a finite set, pretend that the sets Bj are disjoint. I'm only going to do the inequality that T of beta has norm, the operator norm is less than or equal to the norm of beta Q. That's actually, the other part is very easy just by choosing things carefully. So I'm going to take C and LP, and then I'm going to consider C restricted to these sets Bj. The sets Bj are disjoint, and so the sum of the p powers of their norms is the norm of C restricted to the union of the Bj, which is less than or equal to the norm of C to the p power. But now, since W is isometric on the things supported in Bj, this is the same as the sum of the p powers of the norms of Wj(C). And now I'm going to use the Hölder inequality, and I think it's the second step. I take the norm of the sum of beta j Wj(C). I do the obvious primitive triangle inequality, getting absolute beta j times norm of Wj(C). I use Hölder to get Q norm of beta times P norm of the list of norms. P norm of the list of norms is that should be, sorry, less than or equal to norm C here, because that's less than or equal here. Put that in the misrinse to correct. And the other thing is just the Q norm of beta. So that does that claim. And the next one, well, here again is the setup. Here's what we want to prove. The duality is implemented by multiplication of T beta times S alpha. Well, this turns out to be really just algebra. It's true for when alpha and beta are each standard basis vectors and LP and LQ of the index set, simply because of this algebraic statement here. And then you get things for finite support by just doing some algebra, and then for alpha and beta by continuity. Okay, so what next? Well, if you now have a homomorphism from bounded operators in LP to any Banach algebra A, which is not injective and is also non-zero, then A contains the image under phi of these Sj and Tj things, and you get then something similar to the statement of the proposition. The isometry parts are no longer true because phi, I guess I want to assume phi is continuous. I should have said that. But up to equivalence of norms, you effectively get the same thing. Okay, a brief break for a picture. Okay, so what to do with this Cuntz system? Well, here's the proposition again in somewhat condensed form. So now suppose that I have a non-zero, non-injective homomorphism from bounded operators on Liouville LP to bounded operators on some other Hilbert space, some other Banach space Y. So then, because K of LP is the only non-trivial ideal, phi descends to a continuous homomorphism phi bar from this Calkin algebra to bounded operators on Y. And so now I have the elements phi bar of EJ. Remember, those things are in the Calkin algebra. They're a bounded family of 2 to the L of 0, non-zero, algebraically orthogonal idempotents on L of Y. They happen to have isomorphic ranges. And at least heuristically, for any subset of J, you expect to be able to make sense out of the sum of these things over J just in that subset and get some sort of idempotent L of Y. I'll say a bit more about that in the next slide. These things are distinct idempotents. Indeed, the norm of the difference is at least 1 if the subsets are different. There are 2 to the L of 0 of them. But the cardinality of bound operators in LP is just 2 to the L of 0. So this homomorphism phi cannot possibly be surjective. simply because the cardinality of the supposed range is too big. Okay, so here's a little bit more detail there. I've put back the statement of the proposition. We have a non-zero homomorphism phi bar from Q to L of y. So I'm going to now fix one of the indices. I'm going to choose a non-zero element in the range of phi bar of EI0 for actually working with things you want to have norm 1. I'm going to take the closed linear span of what happens when you basically, when you go back with TI0, but then go out with SJ. Oh, that's a mistake. That index set is supposed to be J. At some point, I switched from using I to J, and I missed a few of them. So these things, SJ, TK, let's say, they are basically an uncountable collection of matrix units. And what this does is it sends A to 0 into the range of phi bar of EJ. And using the elements phi of bar of TJ, which I didn't mention on the previous slide, and also this part 4 part with the whoops, there's a mistake there. That equal sign is not supposed to be there. You can actually prove that, first of all, Y0 is isomorphic, although not necessarily isometrically isomorphic to little LP of the index set. And moreover, with a bit more work, it's actually a complemented subspace of Y. I won't go through that part. Time is somewhat short. But now the bound operators on little LP of J are then contained in L of Y. And for the same cardinality reasons, phi bar cannot possibly be surjective. Okay, so what do we really need in order for this to actually work? Oh, I see there's something in the chat. I should look here. Sorry. Oh, I should recopy the, yeah, I'll repost the handout because, yeah, if you arrive after some chat message has been posted, then you don't see what went before. Okay, so I want to do this sort of thing for some other Banach spaces X. And first of all, I want a Schauder basis. For X, it actually ought to be unconditional. And there should be a uniformly bounded collection of isomorphisms from X to the span of, and there's a mistake that R is supposed to be a B. Of infinite, to the closed linear spans of, well, I put all here, but that's really overkill, infinite subsets of the natural numbers. Those are where the things Vj are going to come from. And you don't actually need all of them, but you need enough of them. You need uncountably many of them, which are pairwise almost disjoint. A subsymmetric basis is good enough, but is overkill. And in fact, want to do things somewhat more generally. I instead of using a Schauder basis, I can have an unconditional finite dimensional Schauder decomposition. So instead of, I basically replace the complex numbers times the basis vectors by finite dimensional subspaces. They have to be finite dimensional because I want this to be, I want the products of two of these things to be, when they're supposed to be 0 in the quotient, they need to be finite rank operators so that they are killed by any non-trivial quotient of the boundary operators on X. Also need to do something to be sure that when you take an infinite subset, then you can actually make sense out of this sum of the phi bar of EJ things, which I mean, this is, I didn't rewrite the notation, but this is essentially the same thing as before. And of course, you don't get norm convergence there. You get some sort of strong operator convergence. There are two actually separate issues. First of all, whether you can do it on Y0, which is the span of just the ranges of the phi bar of EJ. And the second thing is whether you can actually do this on the boundary operators on Y. And I'll get on the next slide to how this works. I'm not going to do the details of the proof. I'll just tell you what particular assumption we use in order to make it work. So here again is the setup that I had. You have a Schauder basis. We want a condition which ensures that if you have an infinite set, then you can somehow make sense out of this infinite sum of phi bar of EJ of idempotence, which of course doesn't exist in norm because the norms of these things are all bigger or equal to 1. So we first consider Y0 as before, and then we try to get from there to Y. And so it turns out that what's called a disjoint lower P estimate for some finite P will take care of both issues. I'm not going to do the details of it, but I will say what this thing is. The second issue occurs by ensuring that Y0 is complemented in Y. So for a Schauder basis, this is what this P estimate looks like. It says that when you take scalar multiples of basis vectors, only finitely many of them, just, it extends to arbitrary sums by continuity, then the norm of the sum is bigger than or equal to the little LP norm of the coefficient list. And I won't go through how this actually works. There's some estimation to be done, but okay, so here is what we want. Say a subsymmetric Schauder basis with a disjoint lower P estimate for some finite P. Second part turns out to be automatic for any subspace of a quotient of LP when P is finite. In the P estimate, if P is less than 2, if this P is less than 2, then you have to take this P to be equal to 2. This is something that's, I'm sure, well known to many of the people here. And more generally, you actually get the following. Suppose that X has a subsymmetric basis and has finite cotype. Then X has the SHAI property, that is, surjective homomorphisms to L of Y are automatically also injective. Unfortunately, this does not get capital LP because of lack of a subsymmetric basis. This is the thing which Horvath originally asked. And so we'll tackle that in a slightly different way. I'll use the Haar basis, which consists of the constant function 1 and some things which are basically, you look at dyadic intervals in the interval 0, 1, and then you take functions which are equal to 1 on half of it and -1 on the other half. And I've written some description here. Again, this is, I'm sure, well known to lots of people, and I was a little bit sloppy with the description to avoid clumsy notation. The way I've defined them, they're not normalized. This doesn't actually matter. They don't have norm 1 in capital LP. So there's a theorem of Gamlin and I guess Godet, which says if you have an infinite subset of the, and here I really do need non-negative integers because that's where the indexing started, then the closed linear span of, so there are two indices here. N tells you the length of the interval, and K says which interval you're using. And so I choose for a random infinite subset of choices of length of interval, but for given length of interval, I have to use all of the intervals of that length. Okay, this part here is just some finite set. But if you do things that way, then the closed linear span is isomorphic to capital LP with an isomorphism constant which doesn't depend on the choice of the set of the infinite set N. And so now instead of choosing just 2 to the Aleph 0 almost disjoint infinite subsets of the index set, I'm instead going to choose 2 to the Aleph 0 almost disjoint infinite subsets Nj of the non-negative integers. So that's going to be, that's this. And then my almost disjoint infinite subsets of the index set are going to be gotten by taking, for each of these things, I'm going to choose for every n in capital NJ, I'm going to take all of the corresponding intervals of that length and put those together. These are still almost disjoint because right, there's only finitely many n in the intersection of two of them, and for each n, I've used only finitely many things here. And so the conclusion is that for p strictly between 1 and infinity, LP has the SHAI property. Okay, so here's the theorem again. For p equals 1, the Haar system isn't unconditional. So this problem is left open. Does L1 of 0, 1 have the SHAI property? And there's one other question which I'd like to mention here. Horvath did not get the theorem, this one up at the top, because he would have needed a negative solution to the following problem, which is still open. Is there a non-trivial, I guess I should say, closed ideal in the boundary operators on, and that's supposed to be LP here, sorry, not L1, which such that the quotient contains minimal idempotence, right? If there is such a thing, then the fact that the boundary operators on Y has minimal idempotence does not actually help you prove non-isomorphism. If there's no such thing, then you would get non-isomorphism more or less immediately. Okay, another picture. This one's recent, only from a little bit over a week ago. It's early in the morning. We stayed overnight in somewhere not very far from here, and it's 10 miles away, 10 kilometers away from the nearest road. This was a backpacking trip. That's the end.
Okay, great. Thank you very much, Chris. Thank you for this interesting talk. Do we have any questions? There is some clapping, I see. Yes.
May I?
Okay.
Or
Please, of course.
Yes, go ahead.
So, Chris, have you thought about continuous functions on 0, 1, or that was not at all in the scope of your study for Psi?
No, I have not. What sort of bases does it have? I don't actually know. To think about it, that's the first thing I have to check.
Yeah.
Well, you can work with the Cuntz set instead, because of Banach spaces, they are isomorphic, and well, then it is easier to understand the shadow base. Some shadow bases.
Yes. Okay. So for that, okay. Now there's an issue though, because we needed this disjoint lower p estimate for p finite, and that one doesn't have it.
Sure.
Plus, of course, no unconditional basis also. So
Yeah.
maybe there are multiple.
It's not unconditional either. Okay.
You know, multiple difficulties with that compared to LP.
Yeah, I mean, it looks very tempting to do. Well, yeah. But again, the structure of a basis you write down isn't going to be very nice. I mean, the thing with the nice structure of basis is little c0, but that's already done.
Yeah.
Yeah, but even if you look at even smaller compact metric spaces, like omega to the omega,
Yeah.
already there are difficulties.
You can prove that it has sort of separable Psi, but that's not very interesting. So if the target space is separable, but that's easy.
Well, yeah, because it's still open, right? That surjective homomorphisms from B of X onto B of Y preserve separability. We don't know that.
Yes. Yes.
It's very annoying because it's a very simple looking question. It should be known.
Well,
Okay,
equally this. Sorry.
Please, Spencer.
this what Chris mentioned in the penultimate slide, the last open problem about the lifting idempotence, or actually existence of minimal idempotence, is sort of what we encountered with Tomek in our paper. We looked at long LP spaces and we could not. We also had to go through different methods than in my first paper, because we just couldn't handle this obstacle what you mentioned here in the very last problem.
I mean,
So.
I'm really a C-star algebraist and now starting to be an LP operator algebraist. So I'm really very naive about what to expect. I mean, there's all kinds of, right? Banach spaces are very unlike Hilbert space. The invertible group of the bound operators on little LP1 directs on little LP2 is not connected. All right, this is a very simple Banach space. Just sort of one step away from maybe two steps away from a Hilbert space. Drastically different behavior. But in any case, it would certainly seem to me that the answer to this problem ought to be negative. But that's very naive.
Maybe I can use this as a clue to give a little bit of an advertisement for the upcoming talks, since you say that little L1 directs from little L2 is a very simple Banach space and not only two steps away from a Hilbert space. Because if anyone comes along to the special session on Friday, then I think we'll hear a lot more about how complex that Banach space is. I mean, indeed, that you have two to the continuum many closed ideals of operators on it. So I mean, you do think you make a very small step and suddenly things really become a lot more complex for you?
Yes, it really is only two steps away from a Hilbert space, and nevertheless extremely complicated. Even just little LP, which is one step away from a Hilbert space, the collection of isometries on it, invertible isometries, let's say, is drastically smaller. And unlike the unitary group of the Hilbert space, that's not connected. I guess it's known the invertible group is connected, but the isometries are very far from it.
And also looking ahead to the special session tomorrow, of course, we will have Bence Horvath speaking, but also Max Arnott, and I hope he may be able to address the topic that you didn't really enter into in this talk, the one that the property that was formerly known as I have, but I understand is now called incompressible. So about whether injective bounded homomorphisms out of a Banach algebra are automatically bounded below.
Yeah, we switched to incompressibility because it sounds sort of reasonable, but we changed some things. I mean, it comes from several different directions. My original interest in incompressibility was the hope that it might actually be a characterization of when, in some sense, there are several possible senses, it seems, an LP operator algebra is C-star-like. I believe this is now false. I believe, but have not written down enough to actually be sure, that there exists a non-self-adjoint subalgebra that bounded operators on little L2, which is simple and isometrically incompressible in the sense that contractive injective homomorphisms are isometric. And so I had originally conjectured that this would imply you had a C-star algebra. And when that failed because of quotients, I extended the conjecture to say that if it was true for all quotients, you had a C-star algebra. And now I'm persuaded that even that conjecture is false, which is, it would have been a very lovely theorem if true, but such is life.
Okay, great. Thank you. Any other questions? No, I can't see any. Yes, so let us thank Chris once again for this wonderful talk. And we are going to conclude this session now, and see you tomorrow. Thank you very much.
Okay, thank you.